This video is going to show how to solve second order differential equations that have the same degree. What do I mean by that? I mean equations that look like this one here. Now we know how to solve equations that look like this, where I've just got ordinary constant coefficients here, a, b and c. What's the difference of the ones at the top? Well, rather than just having an a here, I've got an x squared, and here and the b, I've got an x. And we need to reduce them from this top form to that form there, and then we can solve them. We're going to do this reduction using a substitution. But first, we need to be absolutely clear what we mean by same degree. So here's the equation. Let me suggest that I used a trial solution, which y equals x to the 5. Well, this term cy would be cx to the 5. And if I looked at the next term along, bx times dy by dx, what would that become? Well, I get my bx, then I get my differential, and the differential x to the 5 is going to be 5x to the 4. So what do I get? When I tidy that up, I get 5bx to the 5. And if I look at my third term here, all my terms on my left side here, ax squared times the second differential, well, I've got ax squared times second differential of that, so differentiating that one down, I would get 20x cubed, and when I tidy that up, I get 20ax to the 5. Now, what's important about all of these? Can you see here that all of them have got a power of x to the 5, all the terms on the left hand side. So this equation is called, it's one which has got the same degree. So when you say degree, you can think about power if you want. Okay, so let's see how this works. Well, it all hinges on this substitution, x equals e to the u. And if we do that, we're going to get an answer. I'm going to do a little bit of prep work here because there's some things we need to do. We need to convert our whole equation then from being in dx and with x's in it into u's and du's. So first step in that, let's differentiate dx by du. Of course, that's going to be e to the u, which is just going to be x. So if I now want to find out what dy by du is, which is where I want to end up, I can use the chain rule, can't I? It's going to be equal to dy by dx times dx by du. We already know what dx by du is, equals x. So just changing the order here for my answer, I find that x dy by dx equals dy by du, which is really useful, isn't it? Because I found a transform for x dy by dx, which I can use later on. Second one I need to do is I need a transfer, so a transform of a dy by d2y by dx squared. So let's just take what I had just now, which is, and I need to start with d2y by du squared. Well, that's differentiating dy by du. We've already worked out what that is. It was x dy by dx. This is all in terms of x and y. So I want to differentiate dx, which means I need to use the chain rule here. So I'm replacing this du with that term there. And dx by du, d by dx, there we go. And I know what this first term is, it's just x again. So all I need to do now is to differentiate, do the differential of this bracket, which using the product rule here, that's a u and that's a v, is going to give me these two terms here. There we are. And when I multiply through by x, I get this here, that d2y by du squared equals x dy by dx, and x squared to d2y by dx squared. Now I need a bit of more tidying up here before I move on, because I want to find out what that is, this term here, in terms of everything else in dy by du sort of form. Well, this bit isn't in dy by du yet, but we know from our earlier work that x dy by dx equals dy by du. So everything now else is now in terms of dy by du. Rearranging, putting that on that side, I end up with this equation. X squared d2y by dx squared equals d2y by du squared, take away dy by du. So I've now got all my building blocks now to solve this equation at the top using those three facts. because I've got something that I can replace this with and with that with. There we are. So let's do that, shall we? So the first term, x squared dy by dx squared, well, that equals this here, so I can substitute that in. This term here, the middle term, dx is x dy by dx equals that, so I can sub that in its place. There we go. So if I now try and tidy this equation up, well, I've got a dy by du squared there. I've got two terms with dy by du. Here's a +4 as a coefficient and a -1. So I end up with 3 dy by du, and this final term doesn't change. What have I got now? I've got a nice, well-behaved second order differential equation, and we know how to solve that using auxiliary equation to find our complementary function. So I'm going to say that y equals e to the z. I'm going to think it might be a complex number of u, and that's my auxiliary equation as a result. Z squared plus 3z plus 2 equals 0. So my roots are real here, aren't they? Two real roots, -1 and -2. So what am I going to do with those? I sub those into my complementary function, don't I? This here, and I get this form. So I get a e to the -1 u and b e to the -2 u. Now, what's different? Everything to this point is just like we've done before in terms of solving. But I need to get back to x, don't I? So x equals e to the u implies that u equals the ln of x. So I need to replace these u's with ln's. There we go. And I get this expression now. Now, some of you may have noticed that if I've got e to the ln of x, well, e to the ln of x is just x, isn't it? And then I've got a -1, so I've got a power -1. So this is actually x to the -1, isn't it? That's a x to the -1, and that's b x to the -2. So here's my solution. Y equals a over x plus b over x squared. So now you might think, why don't we just use that sort of approach in the first place with just putting in y equals x to the n and finding our solutions? Well, there's a bit of a complication when we look at our other solutions, so let's have a look. Let's go back to our original equation. There's our original equation. We use the substitution. We translate that equation, transform it into an equation in u, and we've got an auxiliary equation that looks like that. Now we've got three situations, haven't we, depending on our discriminant. If we've got a positive discriminant, we get two real roots, lambda1 u, lambda1 and lambda2. We substitute them in there, and when I convert them, as I want to, into e to the back into x using that substitution, u equals ln x, I end up with a nice neat equation solution that looks like that. X to power lambda1, x and x to the power lambda2. But what happens if I get work with auxiliary equation where the discriminant is 0? Well, I get a repeated root. Here's the repeated root, lambda u, but I have to have an ax plus b. I would normally have, wouldn't I, an ax plus b term. Of course, now it's a u. When I substitute back in here, I get this situation here where I've got a ln x plus b, and then I've got a power here on the end, x to the lambda, for my repeated root. So I've now got a ln turning up here. Okay, and what if I get complex roots? If my discriminant is less than 0, I get complex roots. The real part generates an e to the lambda u. So here I'm assuming that my complex solution z equals e lambda plus omega I. Yeah, it's not very coming through very well there. So I get my real part, and then I get my complex part creates the cosines, doesn't it? Cos and sine, that should be a b sine, shouldn't it there? What's the problem? Well, interestingly, I've got an omega u in the bracket here, and when I substitute back for the u equals ln, I get this crazy setup where I get a cos of omega ln x and a sine of omega ln x. There we are. So I think that probably shows you that I can't just go with the x to the n solution. I have to work through this substitution here and then see which one of my solution types I get. So here we are, final summary. If I have an equation of this form where every term on the left hand side has the same degree, think about the fact that I could actually have an extra term here. I could have a, excuse me, I'm going to have a quick, I could have had a x cubed term, couldn't I? D cubed, dx cubed, that would have the same order. So I could do the same thing for a higher order equation here. But if I use this substitution here, I will get a well-behaved differential equation that looks like that. I can then solve that in terms of u, y in terms of u, and then I can sub back into u equals ln x to get back to x. So there you have it. Best of luck.